Thanks, everyone, for coming to have a discussion about the future of caches in our storage systems or in our key value stores or in middle systems. So today, my high-level topic is going to be about auto-scaling caches, also known as self-optimizing caches. Right? Well, my picture has gone gray after. It goes with my hair, I guess, slowly. So a little bit about myself. My name is Irfan Ahmad. I am a co-founder for a new company called CachePhysics. Prior to this, I built, as a founder, a company called CloudPhysics. So you can see there's a little bit of a physics envy in the companies I'd like to work on. And that company is 7 years old. It's still around and doing well and growing in Santa Clara. Venture funded by Kleiner Perkins and lots of big customers. Prior to that, I spent almost a decade inside VMware, where I worked on the kernel, on the ESX, as well as distributed and dynamic resource management, so making sure that applications receive the resources that they need in an autonomic way. And before that, I was at Transmeta, and I published in lots of storage and systems journals and conferences on the academic side as well as on the patent side. So the company that myself and our team has worked on is really focused on data path monitoring and modeling software. So everything I'm going to talk about, you have to think about it from algorithms and then in software, right? So the algorithms part can be implemented inside hardware, inside firmware, as well as inside silicon. And then the software part that I'm going to talk about is focused, obviously, on easy deployment inside kernels, storage systems, and et cetera. And our focus is to provide real-time predictive modeling of data access patterns. So what is the access pattern that your application is issuing and that your storage system or your key value store is receiving? Okay, and how can we exploit that for lots of different goals, optimization, cost reduction, providing latency guarantees, throughput guarantees, and things like that, right? Okay. So before that, just as a preamble, we all know caches are critical to every application, and I always like to say that there is no such thing as a distributed system without a cache. That's the only way distributed systems can be built, plain and simple. We've known that in computer architecture and processor architecture for a very long time, and hence if you look at the surface area, die area of a modern processor, you will see that a huge chunk of it, if not half in some cases, is actually covered by last level caches, which are kind of like a little distributed system, right? Lots of cores communicating with each other and then caches in the middle. So the same thing happens in a data center and in a modern application. You've got databases, key value stores, containers, applications talking to each other, typically on some sort of a distributed platform, either cloud platform or a internal private cloud sort of thing. Underneath the surface, of course, it's still servers, CPUs, caches, disk drives, storage arrays, and DRAM. So throughout all of these layers, there are caches. And today, the state of the art in monitoring and understanding the behavior of these caches is really kind of one number. Right? And you've all probably already guessed what that number is. It's what's my hit ratio or my miss ratio at this moment. Right? Or maybe if you're really lucky, you've got a dashboard that actually plots that over time. So now you've got a time series of your hit ratios and miss ratios. But there's a lot of kind of insight that's missing. There are some questions that, despite the fact that the caches are so critical to the system, are very, very hard to answer today. And so let me go through just a couple of them, right? So you get that 65% hit ratio in that little black box that I've mocked up there in a potential dashboard. Is this performance good? It's hard to kind of answer that. Well, if it's good, is it good? Okay, well, maybe it's good if the application is not complaining. But could it be improved? Right? What does it take to improve it? It's hard to answer that question today. Now, I won't do that today because my time slot is very short, but in the past, when I've given this talk, I've actually kind of asked the audience to kind of participate in trying to figure out answers to this question, and we often end up being fairly stumped. And the reason why that happens is that, and the reason I ask the audience for what the reason is, for why it is that we're not converging on an answer, typically they'll say, well, it depends, Irfan. You cannot just put that question on the screen and expect us to answer it because it depends. And that's the gotcha, right? It depends. It depends on so many factors that it's very hard to answer. So I'll go down to the bottom, right? What if I change cache parameters? If suppose there is some kind of cache thrashing or pollution that's happening between workloads, right? How do I model that? How do I understand it? And then how do I mitigate it? So these are just some sample questions that are very, very hard to answer today. But if we could answer them, we can do some amazing things. So that's what we're going to venture to do today. So I will posit that modeling cache performance is the same as plotting a single curve. If you can plot this curve, you have actually solved all your cache problems. Okay, that's a very, very general curve. So on the left-hand side is the state-of-the-art today, which is that dashboard, fictitious 65% hit ratio at the moment with a certain cache size for your cache, for your workload, and so on. Okay? On the right-hand side, what I've done is I've plotted that 65%. Now you'll see the y-axis is latency in this case because I did the translation while preparing these slides into latency. But really, latency and hit ratios are going to be very close to each other in the sense of they'll behave similarly, right? And we can talk about why that is in a minute. But what I've done is I've drawn a little dot for where the 128 gigabyte mark is and where the equivalent latency for that system is at 65% hit ratio, okay? So far, so good. So this is not modeling. The modeling would be if we wondered that dot, like what if we added more cache? Would that dot move to the right? Would it move down? Or would it just stay flat? That's the question we want to answer, right? What if we reduce cache size? Would that dot move up? In other words, would latency get worse? Now, if you can answer that question, we are pretty far along in knowing how to really deal with these caches, okay? So in other words, what we want to do in the entire exercise of the last 50 years worth of research in the area of modeling caches boils down to something very simple. You want to learn the performance model of the application and the cache's behavior for that application, right? This co-model. If you can figure that out, that's the same as predicting the performance of the workload as you vary the parameters. Cache size is the one that I've modeled on the x-axis here. There's lots of other parameters you can model on the x-axis, right? Not just cache size. But this is the easiest one to talk about. Okay, so if you have a little brain in the middle and it can learn the performance and draw it as a function, then of course all that is for that particular combination of application and cache, that's that blinking curve. Now, the reason why I make it blink is to emphasize that that's not available today. Like, if we had that today, I wouldn't need to give this talk. Right? No system today in production gives you that curve. Right? You could have a storage array that has a workload hitting its controller, and the cache is behaving the way it is, but it doesn't give you this little nice diagram to say, hey, by the way, you're operating here, but if you were to change parameters, and I'll talk about what the parameters in a storage array are, obviously you can't change the cache size all the time inside a storage array. We'll spend a lot of time talking about what you can do. But if you're running, say, a memcache or a Redis cache, right, these are things you can very quickly scale up and down. So this is not available today, but that curve is what we call a miss ratio curve, or more generally, a cache utility curve. Okay? Because as you vary a parameter, it tells you right off the model, the prediction, what the performance is going to be before you make a change. Now remember, this is not changing production in 1,000 different configurations to figure out what the curve is. Can't do that. That's too difficult. That's too dangerous. This is just purely based on modeling. So far, so good? Okay, so now let's talk a little bit more about that curve, because the rest of this time is all going to be about that curve. Okay, so we need to really make sure that we all understand that curve. Please ask questions. Please, please, please ask questions. Okay. So now, again, in this case, I'm modeling cache size on the x-axis. We will see other situations where we model something a little bit different, and the latency on the y-axis. So first thing you'll notice is lower is better. Okay. But adding cache doesn't always result in an improvement. Why is that? Why is it that you see these flat regions? Why do you guys think that we see flat regions? We're adding cache. Let me give you the example. Like, okay, we double the cache. Do we see a performance improvement? No. Okay. Yay, audience participation. First person. No, this is going to get viral. You watch. You start this, everybody follow. Okay. Now, let's say we 4x increase the cache size. Performance change? No. Now, we know that because we know this curve. Right? But if you're a poor person sitting in production trying to figure out how to improve the performance of this workload, you might go through that. You might even 8x increase the size of your cache and not see any performance improvement. You may give up at that moment in time. I wouldn't blame you. But we will all be laughing at you because we will see that you just stopped right at the cusp of improvement. Right? From that moment on, every single byte of additional cache that you will invest in this workload will pay itself back. How do we know that? Because we see latency dropping as part of our prediction as you add more cache after that. So again, let's go back to the question. Why is it that these flat regions exist? Take a guess. We won't ask you to name yourself. So there will be no record of whatever it is that you said. Why are there flat regions? Why is it that I can add cache and get no performance improvement?
The size of the active data set is larger than the cache, and probably too many releases.
Perfect. I did not pay him. He just came up with that on his own. It's a perfect answer. The man in the yellow shirt wins. So exactly. So let me just repeat in the microphone. So as we were, the working set, the active working set for that application didn't fit. So what happens when active working sets don't fit? There's a term often used for that. Thrashing. The man in the dark gray shirt. Thrashing. So what's happening exactly? That's thrashing going on, right? So while you're thrashing, you can add whatever you want. It's not going to make a difference. You're just wasting money. So now we start to see, okay, this is a very, very powerful curve because it tells you the useful increments of change. Right? If you're going to make a change in your system, what are the useful increments of that change? Make sense? Okay. So we'll stay with that workload. By the way, the workload that I'm using this example is actually a production workload. It's not some benchmark test. It's a real customer production workload. In this case, it was a SCSI workload. And so now we look at the same one, but we say, okay, well, I want to get a bit more sophisticated. I want some mathematical way of knowing what those efficient operating points are. Any other point other than those three where those arrows are ending up is an inefficient operating point because it's not giving you the maximum bang for the buck. So you'll also notice something else about the bottom, where the arrows are pointed, they tend to be at the bottom of these cliffs, right? Because that's where the biggest delta is, right? So if you're at the bottom of a cliff and you add a little bit more, you don't get much. Because now you've fallen to the bottom, right? You have to roll all the way over the next hill to get the next increment of benefit. Does that make sense? Okay. So we haven't talked about how these curves are generated. We'll hint on that a little bit, but most of the time today I want to focus on why is this type of modeling useful? What can we do with it? And then we'll talk a little bit about how to go and generate that. Okay? So interject with questions at any time. Okay, so now let's look at some more examples of these cache utility curves or miss ratio curves. So here's a bunch of real production workloads. Some of them are from our customers, and there's three on the top left that are from a publicly available set of traces from Microsoft Research from a few years back, which are quite useful because they're very nuanced and very hard to model. So we always try to include those in our tests. Okay, so these are sample production workloads that we have computed models for, and there's a lot going on in these curves. I'm not going to really bore you with all of those details. Happy to go into them individually with you offline. But for T05, and of course these are anonymized because our customers don't want us mentioning their names or workload names, et cetera, right? So T05 here, I've highlighted that one because you'll see that generally speaking, for three different cache policies, right? So cache policies are things like LRU, LFU, ARC, LIRS, and so on. I just picked three different ones. Okay, you'll see that there's actually a significant difference between them. Depending upon which cache policy you pick for that workload, it's a huge difference in performance, right? Of course, the blue one should be ignored because that's the oracle, right? There's no practical algorithm that can achieve it. So that's the best possible for any algorithm in the world, possible ever, provably, right? So the other algorithms are trying to get close to it, but there's a difference between them, right? Also, T05 illustrates something, which is that for that workload, right, the most of the benefit comes in the early little bit, right? You give it a few gigabytes of cache, and you get most of the performance. After that, yeah, you can keep giving more, but you're not going to get as much of a return out of it. Now let's look at a contrast. Let's look at T19. In that one, of course, the oracle, which is the bottom curve, the lowest curve, the best performing curve, which is not a practical algorithm, cannot be achieved. But the other practical algorithms are trying to get close. But again, there's a huge difference between them. And what you'll notice is that for quite a while, there's a kind of a little bit of a flatness and then a cliff. And that means that at 400 and maybe 500 gigabytes, right, that workload's working set just fit. And boom, you got this huge improvement in performance, right? Okay. And then the final one just to look at is another example where the difference in the way the algorithms are has just a remarkable magnitude of impact on the performance of that system, right? Okay. So hopefully we're getting warm with these curves, what they are about, what they help us do at the kind of very high level, and then we'll dig deeper. Question?
How do you get the blue curve, the optimal one?
So that's actually really interesting. So when we first started working on these techniques, these algorithms that actually do these models, right? the only way to get the OPT curve was to run OPT actually, which is very, very slow, for every possible cache size and interpolate, right? So it would take like a week to run the OPT experiment for any of these traces, literally a week, right? Later on, we came up with improvements to the algorithms that we are now commercializing and licensing to storage partners as part of our offering, where we've actually figured out how to run that one as well in a few seconds, which used to take a week, now runs in a few seconds. And so basically, in that case, we're doing a whole bunch of parallel simulations to figure that out. Sorry, say again, please? For every workload, yes. And the nice thing now, again, is that even OPT, which was resistant to any type of acceleration in terms of this modeling, is now down to a linear. All these used to be nonlinear, and our technology is the first one that allows you to make it linear. So now, yes, you could if you wanted to. Now, we wouldn't recommend doing this in production because OPT is still more, even though if it's a few seconds, it's not milliseconds, right? And the other ones can run in a couple hundred milliseconds for weeks at a time. So, and I'll explain that more in a minute. But yeah, so we wouldn't recommend running the OPT model. It's just here for illustration to see how much the difference is between policies. Great question, though. Okay, so now I want to, again, these are very, very heavy graphs. And so this talk is super technical, and hopefully you guys like that sort of stuff. And so there's a lot going on here. The only thing, and then we'll come back to this curve in a little bit. The only thing I wanted to show you is that not only is it that different workloads behave differently depending upon how much cache you give them and how you configure them, but also that curve changes over time. Okay, so we're not going to spend too much time on this, but what we're going to do is just going to let this animation play out, and don't worry about any of the vertical horizontal curves. Just look at the main actual miss ratio curve, and you'll see it's changing. Right, so it's not enough that you just model that pattern and those cliffs and so on one time. You actually have to keep up with it because things change. So for example, here you'll see all of a sudden this workload just got super heavy and its characteristics changed. Most likely was some web traffic hit this server, and all of a sudden the query mix changed and the curve just takes off, right? Imagine the flatness that just evolved with this curve. And then after a certain number of days or a week, right now, because this is very heavily sped up, and now what you see is the curve kind of slowly coming back to its previous working set behavior, right? And you'll see it kind of convert to where it started. We'll spend more time on these curves. So all I want you to take away from it is those curves, they're not static, they actually change. There's an additional dimension, which is the dimension of time. Okay, does that make sense so far? Okay. Okay, so now I promised that there are lots of things that you can do with these curves. I want to start to talk about one of them. So let's start with online modeling of policies. Okay, so this is a very interesting curve on the right-hand side because it's the first time you're seeing multiple miss ratio curves in the same plot. So all of these miss ratio curves are for the same virtual machine workload. So you may ask, well, Irfan, well, how can a single virtual machine have this many different curves? So what we did in this case is that for each of those curves, we modeled a slightly different behavior. And the parameter that we changed between those curves for the exact same workload run in real time simultaneous with the workload is that we changed the cache block size. Now, how many people have experienced running storage arrays or have built or done software development for storage arrays? Maybe about 30-40% of the room? Okay. So as you know, your storage array, the one that you operated, probably has a parameter called cache block size. And why that's important is typically workloads running, let's say from Windows or Linux or some application or database, are pushing reads and writes into the storage array with a certain size. Make sense? Right, it used to be, for example, that DB2 had this like 2K block size, and if you had a cache line size that was 8K, you were wasting 6K worth of random space in the cache, and that was a huge problem, right? Well, nobody knew how to tune that other than just playing around with it, right? Now, if they had these curves, they'd be able to tune it exactly. So now what we did here, again, is that we plotted simultaneously with the workload all of the possible different cache block sizes, which is just a parameter. You go to the user interface of the storage array, and you flick it, and it changes, right? For the same workload. And what we see is a remarkable pattern here. So even for the same workload, depending upon what miss ratio that your SLA target is, the optimal block size changes. And so the black one I've plotted here is just, I just took the minimum of all possible curves to just show you the crossovers between them, right? Sometimes it's the purple curve, sometimes it's the green curve. And what that means is that sometimes in some parts of this regime, the best performance is achieved with 4K versus 8K versus 16K versus 64K. Even if there's a regime where it's actually 1 meg is the cache block size, that's the optimum one. Okay. So now the other thing this shows is that forget the trying to achieve the optimal. Like, what are you going to ship with in this default in your storage array? Right? If one workload can have this much variation, imagine thousands of workloads that you have to handle. How are you going to figure out when you ship your storage array, or when you configure it if you're in a deployment, if you're in an operations team, how are you going to figure out how to configure that parameter? Right? Today you just can't because you just don't know. Right? And so again, these curves would allow you, these kind of models would allow you to do it. So there are other parameters that you can vary and then build this multidimensional optimality for, and I've listed some of them here. So for example, you'll see under examples of policies, you'll see a cache block size, the one that's plotted here. You'll also see use of subblocks. Some storage arrays have the ability to use subblocks. Write through versus write back versus not write invalidate in terms of policies. That makes a difference in performance, actually. And so now we can actually model each of those three as different curves, plot them on the same graph, and we'll be able to draw the optimum. Write buffer size is an example of this. A size of read versus write cache, a classic problem in sort of multi-controller situations is if you're mirroring the write cache, right, how big do you make that versus the read cache? This is parameters you can easily change in a user interface or via an API of almost every storage system you use or that you've built. But there hasn't been a good way to figure out for particular customers or particular applications needs what those parameters should be, right? And now we can just plot them, right, as curves and then pick the one for that exact workload. Does that make sense? Okay. And there's lots more to talk about here. So now so again, we're still in the realm of these mixed ratio curves. And now we're going to go into some examples of whether these parameters that I talked about, just, hey, plotting and picking, well, can we pick them optimally at runtime with no hint, with no human intervention? Okay? So now in this particular case, what we're plotting is a real production customer workload running in an environment where LIRS is the cache eviction algorithm. So you're familiar with LRU, LFU, probably you've heard of ARC. There's another one, really, really good one, very competitive with ARC, in many cases much better than ARC, called LIRS. It's public domain, published 2002 timeframe. And so, however, just like every cache algorithm, it has some parameters, right? And it's very sensitive to those parameters. So what we ran an experiment here was, in collaboration with the LIRS team, was to try to figure out if our algorithm could optimally find the perfect parameter without knowing anything about the workload ahead of time, right? This is kind of like a man versus machine sort of a thing, okay? So the man part of this is the dotted lines, because those are the ones handpicked based on some high-level thing of the best that could be done in a static analysis. And then that's a top one, the blue dotted line. The black dotted line is black dotted line is the best. The blue is kind of the worst that's possible based on static analysis, right? And so we were trying to find out how close a completely hint-free system could get to the black line. And so these are two examples. The left one is the best one in all of our traces. We traced the optimal perfectly. Okay, what that means is we found the perfect combination of parameters in the cache algorithm and implementation to operate at the sweet spot. And then the rightmost one, the LIRS MSR proj, is the worst one in our entire test set for this experiment. As you can see, even in the worst one, right, we track pretty closely, and there's a few places where the online no-hint algorithm gets a little confused, and we're still working on improving those. But either which way, right, it's a huge, huge improvement. Does that make sense? Like I was varying parameters, but not telling the algorithm anything about those, and it had to figure it out completely on its own across lots of values of those parameters. Okay. Here's another one I won't go through, but it's in the slide deck for your review later, which is a different cache algorithm with more complex parameters, and see how close we got. And again, we got very close to the optimum in this case as well. Okay. Now, we started this conversation almost right at the beginning by asking a question, the answer to which was thrashing. Okay, so what was the question? Why doesn't the performance always improve when you add more cache? Okay, and the answer was thrashing. So now the interesting thing about thrashing is that throughout the history of caching, right, we just had to deal with it. Thrashing is just a fact of life. You can't do anything about it, right? That's what we've learned in school. That's the way, when we do testing for our systems, that's the way it's always been. You just cannot do anything about thrashing. You have to just try to figure out if you are thrashing so that you can try to maybe add more space or try to mitigate in some way, right? Maybe move workloads apart or something like that. But up until now, it's never been possible to come up on a stage like this and say, hey, we can actually kind of do something about thrashing. Okay? So it turns out that you can do something about thrashing. But to be able to eliminate thrashing or to do thrash remediation, in this case what I call cliff removal, you first have to be able to draw the red curve, which of course we know how to draw now because we have this technique to be able to draw Mr. Ratio curves efficiently and in real time. Okay? But once you can do that, first thing you are able to do is, because you see the cliffs, you can draw the black dotted line, which turns out is mathematically the convex hull of the Mr. Ratio curve. Okay, now this is getting a little technical. But what that means is that the best possible algorithm, right, maybe could sit on that convex hull. Can't get better than that. Okay. So now then the quest started to try to figure out, hey, okay, if we can mathematically draw that convex hull, it's really easy. In the convex hull is just kind of draw the lowest points of the lowest parts of the cliffs. If we could draw the convex hull, does there exist an algorithm that could operate at the convex hull? Okay. So that search led to some very interesting results. And basically, the way it works is that you take your existing algorithm. In this case, this is LRU, right? So most storage systems are running LRU, standard LRU, right? So this is nothing special about the algorithm here, just straight LRU for the red curve. Now, suppose you could steer part of the input into this LRU and treat it a little bit differently. Okay, what would happen? So here's what happens. And this is a paper published in HPC 15 that uses the interpolation of the convex hull. So I'll explain how it works. So let's say right now you are in the middle of that thrashing period, which I think is about 50 or so gigabytes on the x-axis, right? So let's say you're operating there right now, and you're in the worst part of the thrashing, right? You're not getting much improvement. So maybe what you could do is just say give up and go to the left, which is about maybe 37, 38 gigabytes, and say I give up, right? Or if you really need to try to actually get a real performance improvement, right, you're going to want to operate at the convex hull. So what we do is we have your system, your cache system, actually internally, without telling anybody, it just hides it, right? It creates two caches. So if you have a 100 gigabyte cache, magically, without telling anybody about it, you create two 50 gigabyte caches, for example. But what you do is you allow the size of those caches, the two caches, which for now I'm just saying is 50 gigabytes, you allow them to be varied. So let's say 40, 20, 10 at runtime. Okay. So that's the only magic you need in your implementation to have this shadow, this hidden partition inside your cache, and just two, not a lot, and just to be able to vary them. Okay. So suppose that you had that. What you would do then is that you would steer part of the incoming workload into one of the partitions and part of the workload into the other partition. Okay, so that's all we do. But so how does that work? So if you start with the 50 gigabyte and 50 gigabyte example, right? I guess in this case it would be the 25 gigabyte and 25 gigabyte because you have a 50 gigabyte overall size. So let's say 25 and 25. If you start with that, the dot doesn't move because half of the workload is seeing half of the cache, right? So let's say you got 1,000 IOPS coming in, 500 go into one partition, 500 go to the other partition. Well, half goes to half, no change, dot doesn't move. But suppose what you do is you send half the workload to a very small part of the cache. Then what happens is that part of your workload moves to that alpha point, right? Because it gets worse, because it got a smaller cache for the same amount of workload. So what happens? Thrashing keeps happening. But luckily in our case, we're on the flat region of the curve. So by making part of the workload behave worse, it actually didn't behave worse because it's already in a flat region, right? So if you look at where the blue dot used to be, it didn't change in performance because the miss ratio did not change. However, the other part of the workload got over a hump, and that's beta point. You see what happened here? Part of the workload got no reduction in performance, even though we kind of stole cache from it. And the other part of the workload got a huge boost in performance because it was able to fit. And turns out that if you do those things, remove cache from a part of the workload, add it to the other, that the average performance of the system now operates at the convex hull. Okay, and this is a brilliant mathematical invention that just magically out of thin air gives you new performance that you never had. For the same amount of dollars, you just in this case, probably got a 15% performance improvement in your workload. Okay? Now, I went through a lot of details there, but ultimately, just think of it this way. There's thrashing going on. You can't do anything about it. But if you know what that red curve is and you're willing to implement cache partitioning, dynamically configurable cache partitioning, you can just go like this and get this huge, huge poof performance improvement. Yes?
So now that you've done the partitioning, how do you decide how to direct your work?
So the question was, once you've done the partitioning, how do you decide how to direct the workload? And it turns out that for the scheme to work at all, you have to do it randomly. Otherwise, it won't work. Because I didn't state it, but there's an inherent assumption here, which is that you don't bias which addresses on the disk or which keys in a key value store end up in which partition. You can't bias that. As long as you don't bias that, it's random, then this result holds mathematical proof. Yes? Please.
What assumptions are you making about the uniformity and the size of the working sets of components of your workloads?
We're not making any assumptions, and the reason why we don't have to make assumptions is because we pick randomly. So if you've got 1,000 IOPS and let's say you've got 1 million addresses on disk, and we randomly pick which of the addresses will end up in which partition, right? You get self-similarity between the two with respect to the working set because we did not bias our picking. So therefore, we have to make no other assumptions other than that one. And that's why the proofs work. Very good question, yes.
But is that implying the total IOPS going into the cache, which the split actually has to be less correlated to each other? Otherwise, it's going to still stretch each other. It's still, right?
Yeah, and again, the brilliance of this, it's a little tricky, but the brilliance of this is that, so remember when we started, we said we have 50 gigabytes of cache. We randomly pick half of the workload and we give it to the 25, and half of the workload we give it to another 25, right? Then performance does not change because the behavior of the cache is just like half the workload into half the cache, no change, right? But the reason why there's no change is because we randomly picked. So now as long as we keep picking randomly, the behavior of any portion of the smaller portion of the workload, okay, is self-similar to the full workload. As long as you pick randomly. It's just like Gallup. When you have a Gallup poll talking to 1,800 people on the phone to try to figure out 150 million voters worth of a result, it's the same sort of thing. As long as you pick those voters randomly that you call, right, there's a self-similarity between the result there and the entire population of voters, right? And the same thing is being applied here. There's self-similarity, and because of self-similarity, we're able to do this trick, which is like magic, right? So I at the top of the slide, you'll see my title. It says New Class of Acceleration, because I kind of ran out of ideas on what to call it. Because caches are accelerators. Caching is acceleration. So when you do an acceleration on top of the acceleration, what is that called? Acceleration squared? I don't know. So I don't know what to call it. So maybe this is a call for ideas on how to name this thing, because it's acceleration squared. Yes? So this is kind of like a realistic one, right? Where thrashing is going on, right? The worst case for thrashing, recall, was the workload that we looked at, which was T08. Now, in the case of T08, imagine the performance improvement that goes from the flat part of the curve all the way to the convex hull, which is the OPT curve point in this case, right? Because in that case, the delta is absolutely massive. It's like from the top to the bottom, right? And so that's a worst case. Now, if you look at T25, you'll see that there is no thrashing. T25 is the one over from the rightmost at the bottom, right? There is no thrashing. So you cannot improve that. So this algorithm, this technique that I'm talking about, it helps you with the worst workloads that you could never do anything with because they were thrashers, and we get them to the convex hull. So it's actually it's helping your worst workloads, which is always nice, right? Because a lot of techniques, they kind of work on the average case. This is helping with the worst case. One question up here.
I was just wondering, the reason you need just two partitions is because you're on the flat part and you want to get to the bottom of one cliff and the bottom of the other? Is that?
That's the reason. That's basically the intuition why you only need 2. Yes, that's right. That's right. Okay. So now, when we started this work, I'll be very frank and honest with you, we had no idea that we're going to be able to do this. We just thought, hey, mixed ratio curves, you can do cool things. You can size, you can pick parameters, you can do dynamic tuning of caches. We had no idea that we would be able to solve like the fundamental problem with online cache algorithms, which is thrashing. You can't do anything about it, right? Other than this sort of a technique, right? So I have to admit, we got lucky with this one. We're not expecting this big of an improvement. Okay, so here are some practical results. Again, the convex hull is the dotted black line. The original is the black curve. And in this case, we're showing for 3 different cache algorithms to illustrate that a hint-free algorithm running completely online has no clue about what the actual workload is going to be in the future. So it has to decide on the fly. It's got no hints at all, right? And that's the red curve. We just wanted to show that it doesn't matter what your incoming work, doesn't matter what the algorithm it is that you're using. As long as there is thrashing going on, we can fix it. And so as you can see, there's a lot of choppiness in the red curve. And the reason is that, again, it has no hint at all. So it has to really online decide these things. And so generally speaking, it converges well. And I think we have some numbers here. So anywhere from 40 to 70% of the potential gain against the optimal in that case, which is a convex hull, is being achieved in a completely hint-free algorithm. Okay? All right. So now we're back to something a little bit more classical on how you use mixed ratio curve, right? And we're going to talk about latency versus cache size in this case. And what we're going to say is, hey, what if you have a customer? What if you have a workload or an application that actually has a latency SLA, right? And storage workloads are notoriously bursty, and they're notoriously have long tails, right? You can easily have a workload that has an average latency of 10 milliseconds, but a 99th percentile latency of 100 milliseconds and maybe 99.9 of a second, okay? So super, super, super power law oriented. So what if you have a workload, like say an ad tech workload, hard deadlines, right? Where you really want to have your storage system plus your cache give you actually some guarantee. So what I'm illustrating here is a 95th percentile latency prediction of the algorithm on the y-axis, and then drawing a 7 millisecond line across. Now, of course, the fact that we have this red curve immediately allows you to draw the intersection, and as long as this algorithm is in control of that cache, right, we can operate at that 7 millisecond point, and what we will be doing in this case is allocating at least 16 gigabytes of cache. Now, when we revisit that video that I showed you earlier, our system actually tries to operate with a buffer in front of that, so we're not going to operate at 16 gigabytes, we're going to probably operate at about 18 and a half in this case, because we want to have a little bit of buffer, because these workloads, as you saw, move, they shift, right, with time. These curves, they change over time, okay? So now, do you guys believe that we can do storage system latency guarantees that you can put inside your storage array user interface and just hold to it and promise that you'll be able to achieve it? Do you understand this enough to know that that can be done? Go ahead. So this is 95th percentile, not average, in this example. Yes, I'm sorry. Oh, did I miss that? Yes. The average latency SLO? Yeah, I'm sorry. So that should not be average, that should be percentile. Yes. Thank you for catching my typo. I'll fix it for the slides that get uploaded. But that's 95th percentile in this case. If your system needs 99th percentile, what you're going to see is that curve is going to stretch to the right. It's going to cost you a lot more money, right? But the working set behavior didn't change. Your SLA changed. So this curve will shift. It will maintain its actual or general shape, but it will stretch, and you should still be able to draw that blue line across and know exactly how to size this thing to hit your SLA, right? So quick poll. How many people think it's important for storage systems to give latency guarantees? Okay, all of you people need to talk to me after. Yes? Okay, excellent. Okay, I'm here all week. Okay, so this is a multi-tier sizing, and I just want to sketch it really, really high level, right? Once you have these curves for your system, really what is that curve doing? It's talking about the working sets, the thrashing patterns, and so on. It's embedding all of those into one curve, right? So now on top of those curves, you can do other cool things, which I'm not even talking about, don't have time to go through today. For example, you can do multi-tier sizing. You can talk about, hey, I have a DRAM and I have NVRAM. Oh, how do I size those two? Right? It's a hard question. It's a very, very hard question. How do I not just size, but how do I then dynamically manage them? And now all of a sudden, let's say I have a consolidation and I've got 5 VMs running on top of this, or 5 LUNs on my controller, and I've got DRAM and NVRAM, and I've got flash, okay, and I've got disk. So how do I do that, right? So these are the sort of thing where ideally what you want to do is you want to encode that sort of logic into the tiering, so that the tiering is actually using these real-time performance models to do its job, and then be able to achieve whatever cost performance target you have. Okay. So here's a kind of a internal UI for how that might look, for explaining what the recommendations are that are being implemented or were done automatically. And so you'll see things like, it's hard to see here, mostly for your reference in the takeaway slides here, but you'll see specific recommendations like, well, given the SLA that you have put into that system, it is not achievable given the working set pattern of your application. You have to do something, and here's what we recommend doing, right? Or that, look, given your SLA is, you're currently like 500x more over provision for your SLA given the last week or month worth of workload. So we recommend that you save some money, right? Those sorts of recommendations just fall out. And we've already done that manually, all of us together in those curves. And it's just, there's some very simple math to go and create recommendations out of that. Okay. So now we're going to go back and look at this a little bit more carefully. So this time, what we're going to do is we're going to focus not just on the changing pattern of the curves. So first of all, the animation currently is on the left-hand side one. So we're not just noticing the fact that curve changes over the course of hours and days. But we'll also start to notice that we have plotted on top of that curve our recommendations, which are constantly updated in real time. Okay, so it's hard to see because the SLO requirement and the optimal efficiency are very far to the left. Now, for both of these, for simplicity, the SLO target is 50% hit ratio, which you'll see as the horizontal line. Now, of course, in your case, it'll be different, and the user would set that, right? But what you're seeing is that as the workload is shifting a pattern, it's going from one regime pattern to another, all of a sudden the curve starts to shift, and you'll see the green curve, which is the minimal required to hit the SLA, the green tall line, the vertical line. And then you'll see the blue-purple-ish line, the vertical one, and that's the one that is adding that buffer automatically and constantly making sure that you have enough buffer that you're not going to overrun. Okay, it also happens to be one of the cliff points, which is how the algorithm is implemented. Now, we went off the chart here, but once that burst is over, all of a sudden everything comes back to normal, and you'll see that the purple line there is again operating pretty far away because of various factors, including the uncertainty of the workload, how steep it is, how quickly it could ramp up, and then looking for the optimal operating points in some cases, and in some cases when the steepness is there to absorb things, right, it gets a little bit closer. So that's in effect how the automation underneath the surface would work for, let's say, a single LUN in your storage controller that has an SLA requirement. Underneath the surface, this is what will be happening. This is the horse trading that's going to be happening per 100 megabyte or whatever your allocation policy is going to be underneath the surface, right? Whereas some of the other SCSI logical units that don't have SLA requirements, right, will be just getting whatever the best effort that they want. Or again, same thing happens in a Memcache or a Redis kind of environment. Whichever client, whichever application needs the SLAs will constantly be expanding and shrinking to make sure that you always hit the requirements for that app, and then everything else will be best effort. Does that make sense? Okay. So the other one, I can just start it while we are having a discussion here. This workload is fairly stable. It doesn't shift a lot, but it does have this cliff, and we're trying to operate at the optimal point under our algorithm so that you have lots of room, and also it's a good balance of cost and efficiency, right? Actually, this one doesn't change as much, but why this one was interesting to present here was that the cliff was kind of close to the SLO target. You see, the first drop in the cliff is close. So it's a test case for us because we want to know if we're able to, even in that corner case where you're really butting up against it, that you're able to, that the algorithm is able to track it. Okay? Okay. Any questions about these animations? Can I go tell my engineer who developed these animations that you guys liked them? Yes? Okay, we'll make his day. All right. Okay. So then, in summary, the first thing we can do using these techniques that I've described today is that we can build these models in real time that allow you to have observability and monitoring in your system, right? Just offer the users of the system the ability to just self-manage, okay? I just want to do the right thing for my workload. If I have the visibility, I'll be able to do it. So that's what we call monitoring or observability. That's the very first use case. The second thing we can do is do auto-select on policies. The example that we looked at for that was cache block size, right? We looked at the parameter selection for LIRS. We saw how close that the online algorithm was able to get, right? So we saw 2 examples of that. Auto selection of parameters, and we all know that storage systems and cache algorithms and cache implementations have remarkable number of parameters. The other thing we saw was latency guarantees. So you can take your storage system, front it with a cache, not have to over-provision the backend too much, and have the cache give you that SLA mechanism. The caches, because caches can be reconfigured really fast, right? And because they are fast, right? If you just have the right control algorithm and right smarts on top of it, all of a sudden you can conjure up these latency guarantees. We also saw tiering. We didn't go into that in a lot of detail. We saw latency reduction from a thrash remediation point, and this is, again, the world first for that. It's very easy to implement inside your existing storage system. We did not get a chance to talk at length about multi-tenant isolation, although I briefly talked about it, which is, hey, if you have a workload, if you have a tenant being an app, LUN, whatever it is, that needs hard SLAs, right? Being able to figure out exactly what portion of the resources of the cache or the storage system it should get to hit those SLAs is not something we can automate. Okay? So the results from all of this is ultimately autonomic tuning of your system. The system ships such that as soon as it starts running in a customer environment, it automatically finds the optimal points. You don't have to send field engineers out. So we have to do kind of finger in the air to try to figure out how to configure that environment, right? A classic example I've heard about this is, a field engineer goes to a customer who happens to be an insurance company, and customer says, hey, how do I configure my storage array? And the guy says, well, I visited an insurance company in Iowa the other day, and they had 8 gigabytes of cache, and they had such and such parameters for their read ahead. Why don't you do the same? You're an insurance company, right? Well, we know that that's broken, but that's kind of, we're forced to do it that way because all we can do is kind of, just do a finger in the air sort of things. We can build latency SLOs. We've seen 50 to 150% efficiency improvements, so bang for your buck improvements in storage systems. And there are operational expenditure improvements, right? Fewer production fires, the ability to actually dial things in and have them be self-managing, and then accurate capacity planning because you can do what if on top of these performance models as well. So some takeaways, this is an award-winning technology. We won a Best Paper Award last year at the Usenix Annual Technical Conference, one of the top systems conferences of the world. This system enables you to deliver optimal cost for the same performance, right? In any scenario, whether it's a thrashing scenario or an optimization scenario. It's the world's first and only latency SLO system with a storage backend and cache combo. So the asks those are the takeaways. The asks would be call for collaboration. We would like to engage with the community on cache performance API standards, both on the key value side as well as on the storage side, so that we can kind of get to a point where this sort of optimization is actually kind of something you can layer on top. And would love to talk to product folks at various companies to try to collaborate on these, as well as integrating this type of technology into your systems. And the applicability for this, for my ask, is database, KV, stores, file systems, and storage systems. So that brings us to the end of my talk. Hope you guys got something out of it. I'll be around the rest of the day. We can chat and talk. Thank you very much for having me.